renewable energy technologies produce sustainable and clean energy from sources such as the sun, the wind, biomass and water. By means of special equipments and systems, it is possible to produce electricity and heat virtually everywhere, provided that the related natural resource is sufficiently available. In recent years, renewable energies have become increasingly important as they are an effective instrument of decarbonization policies and have also become extremely competitive with conventional sources. The main renewable energy sources are solar, thermal and photovoltaic, wind, hydroelectric, biomass. Not all, however, are suitable for building applications. Renewable energy technologies that can be better integrated in building are photovoltaics, solar thermal and microwind. A photovoltaic plant allows for the transformation of solar radiation into electricity. The conversion takes place thanks to the so-called PV cells, made of semiconductor materials such as silicon. In order to be protected from weather and external factors, the cells are assembled into modules. These modules are usually grouped into strings, which in turn are connected to the control and storage devices as inverter, charge regulator and batteries. Photovoltaic systems can be divided into two main categories, standalone and grid-connected. In the former, a storage battery is interposed between the generator and the inverter. Electricity is stored when production exceeds consumption and fed back when consumption exceeds production. Otherwise, when systems are connected to the grid, all the energy that is not directly used on site is fed into the grid. During periods of little or no sunlight, the grid integrates the user's needs. Recently, systems that are connected both to the grid and to storage units are becoming popular in order to increase the possibilities of self-consumption without compromising the security of electricity supply on demand. The electricity produced by a photovoltaic system during a given period can be estimated using this simplified formula. EPV is the amount of electricity produced during a given period in kilowatt-hour. PR is the performance ratio of the PV system, which value is usually in the range 0.75–0.8. PPV is the nominal power of the PV system expressed in kilowatt peak, and S is the solar irradiation incident on the module surface during the period, kilowatt-hour per square meter. The productivity of a photovoltaic system is highly dependent on the climatic context in which it is located. Indeed, its energy production depends mainly on solar irradiation availability, but also on temperature, since the cell loses efficiency as it heats up. As an indicative figure, 1 kilowatt peak photovoltaic system, which means about 7 square meters of modules, can produce between 800 and 1,500 kilowatt-hour electricity annually, depending on installation site. Building integrated photovoltaics represent an interesting opportunity, since the installation of the modules on the building envelope provides a variety of advantages, such as the use of the land surface already occupied by buildings, the savings on support structures, the replacement of materials and components such as traditional roof or facade elements, and the possibility of directly using the energy produced on site. Solar thermal systems convert solar radiation into heat. Their use is compatible with all the applications that require thermal energy at a relatively low temperature, such as the production of hot water, but also air conditioning. Solar energy is captured and converted into thermal energy through solar collectors. The market offers three types of products: flat plate, evacuated, and unglazed solar collectors. In general, we can say that the efficiency is very good for evacuated collectors, good for flat collectors, and satisfactory for unglazed collectors. The most common use of solar thermal systems is for domestic hot water production. But there are also other uses, such as heating or so-called solar cooling. To facilitate the water heating process, the collectors are connected to a storage tank, with progressive recirculation of the heat transfer fluid. Circulation in the system can be natural or forced. In order to limit the imbalance between summer and winter production, modern solar thermal systems are designed to provide about 60–70% of the hot water demand, and an auxiliary heater provides the remaining fraction. The percentage of the demand satisfied by the collectors is called solar fraction. As far as the dimensioning of the systems is concerned, this must be done carefully, taking into account technical, climatic, and utilization parameters. For this purpose, there are practical methods or specialized software, which help to identify the most appropriate solution for the specific case. As a first approximation, it can be said that 0.5 to 1 square meters of collectors is needed for every 100 liters of hot water per day. Finally, as regards the storage, the tank can be sized around 50–70 liters per square meter of collector area. A wind power system consists essentially in a windmill, which, thanks to the rotation of its blades, produces electricity. For building applications, the more suitable devices are represented by mini wind turbines, with power up to 20 kW and rotor diameter not wider than 8 meters. Wind turbines can be of two different types, horizontal axis and vertical axis. In the former, which are the most common, the rotation axis is horizontal and therefore the blades rotate in a vertical plane. A rudder keeps the blades plane always facing the wind direction, and a control system slows down or blocks the rotation speed when the wind speed is too high. Vertical axis wind turbines can have different configuration and shape and do not need a system to follow the variable wind direction. For this reason, they are generally very robust and durable, since they are mechanically simpler. Small wind turbines can be installed on buildings top, but it is necessary to be very careful about possible vibration transmitted to the building structure, which may cause fatigue phenomena and noise. In order to evaluate the electric power that a horizontal axis wind turbine can produce, this formula can be used, where P is the electricity power delivered in watt. Alpha is a performance coefficient depending on the turbine type, ranging from 0.12 to 0.17, and D is the diameter of the rotor, in meter. V is the wind speed, in meter per second.